mRNA technology, so it's quite a different technology. So Moderna's is a different technology. But anyway, I'd be very hopeful by summertime.
Yes.
We'll be moving around again.
Let's all cross our fingers. Hope so.
My system, you cannot theoretically tell it.
Right.
My system doesn't like foreign material.
Yeah, coming to talk about this mRNA technology, it's actually very interesting. It's a lot of technological achievement. I mean, instead of that good old antibody and antigen crude war, all they're trying to do is sending in an instruction to your, essentially in the form of an mRNA, which will produce a protein. And that is a protein which is just the spike protein without a virus behind it. So the spike protein will essentially try to get into your cell, and the cell will be completely lured into making the immunity full-blown. And that's amazing technology. I mean, I was just reading through it, and I just figured that it's just a information technology connected with the biology. It's totally different, and it's amazing. I mean, it has so much of potential to do a lot of good things as well as a lot of bad things. Depends upon what you want to do.
Well, we're going to end up digitized.
Yeah,
that is true.
One can take your theory seriously, but my system is unique. So it's not one fits all.
Okay.
Hey, John.
Hi.
John, I was thinking when I saw you last time, I think it's in Berlin several years ago. I think you were in a meeting that is about the time we had our physical review letters of that silicon 4+ anomaly. If you remember, you and Eugene Kennedy, you did this experiment. And it is just a paper came out, and that's the time I met you for the first time 3-dimensionally, and that's the last time as well.
Yeah, we're back in 2D now, yeah. Yeah, that's a long time ago.
That is true.
Yeah, it's a long time ago.
You don't come to US much, do you?
No, not really. I mean, this is all, well, I spent 12 years on the dark side. Being head of school and dean of the faculty. So to be honest, I'm really only getting back into research. Yes, we had some money and stuff.
You had to wear a tie and things like that?
Yeah, exactly. I had to wear a suit and a tie and all that sort of stuff. And those days are over, thankfully.
Yeah,
so,
I remember seeing Kenny Bell, who became an administrator at Queen's, and I almost didn't recognize him.
Yeah, it has that effect on you. Yeah,
I asked him if he was dressed up for a costume party.
Well, he was.
He was.
I don't think he saw it that way, though.
I mean, they tell you can achieve great things, but you achieve nothing, and you find out that the only things you really achieve are the things you can publish, and nothing else really has longevity. I remember Kevin Carroll, my old prof, who sadly passed away a couple of years ago, and Kevin used to say to me that, well, bear in mind that the only things that you're by the time it gets to your great grandchildren, they won't remember you, so forget about it. So the only thing that lasts after you is your published word, and that's it. And there's the possibility in 100 years' time, some kid is in some holographic information world, which will be the new libraries, and pick up your paper, and they'll be inspired to do something. And so that really is the only immortality you really have is your published word. So maybe. That's why I started off as wanting to be an academic. I never wanted to be an executive, and I was determined to retire as an academic. So
yes, French poets used to make a lot of weather out of that, because there was a French poet who went around seducing women by promising them immortality. You see, if he celebrated them in verse, then everything that you say would have happened to them. However, I'm not sure that this actually leads you very far, you know, this kind of immortality. And anyway, the person you mentioned who might pick up a piece of work you'd done in cyberspace later on, he probably would just read it for a laugh and think, that's what they thought in those days.
Yeah, exactly.
Yeah. You mean like us reading Ptolemy and his view of the universe, the Ptolemaic system, with epicycles. Since the circle was the perfect figure, then everything went around in combinations of epicycles, sort of a proto-Fourier expansion.
Yes, they're marvelous things, epicycles. In fact, you can fit your grandmother's profile with epicycles. And the extraordinary thing is really that when you look at it from that point of view, Ptolemy's method works better than either Copernicus or Kepler. And actually, you know, when people say that you prove a theory by comparing with experiment and finding discrepancies, this is not true, because actually there's less discrepancy between the epicycle theory and experiment than between the accepted theories and experiment. In fact, you know, epicycles, they even fit the precession of the perihelion of Mercury. So relativity is included in the epicycles.
Hey, Pranava, since you are back, can I make a comment?
Yes.
If I look at the current schedule, unless that has changed, I think every session has 3 hours, right?
Yes.
So if there are 20 minutes talk for 7 talk, it's going to be 2 hours, 20 minutes, and we still have 40 minutes left. So I was just wondering that if we keep some questions, I mean, this is also to all the conveners or chairs, that if you can keep a few minutes between the talk or give a little bit of flexibility rather than cutting it off right on the top of 20 minutes, we should not have much problem with the time, because like for example, in the last session, even after that technological glitch, we still saved about 20 minutes. We could have been distributed throughout in between the talks for question and answer and things like that. I think that way it probably would have been a little more relaxed. I mean, I'm just thinking aloud. I mean, you can.
Yeah, actually, the 20 minutes we originally intended to include the question answer. The talk for about 16, 17 minutes, and the 3 hours was just an extra provision.
Okay.
You know.
Okay.
I think that is what we
session, I'm sorry, the last session took the whole 3 hours, even without question and answers.
Yeah.
And there were a few questions on the chat box, and I distributed to the speakers and received answers immediately. It was very sort of efficient.
Yeah. So I guess Alfred is chairing the session, and he'll take the call and, just take it how it comes,
also, If you monitor to keep the clock. My point is, I assume the speakers to keep their time. I would run this approximately so that we can go beyond and adjust things. But we want to eliminate people going way over time. But most of the people who are aware of the time given. I don't like to write, to run a tight ship.
Well, tomorrow we have 9 talks, so it will be tight.
Yeah.
Right,
yes,
right.
That's true.
If it is 9, then it's a difficult.
Yeah.
Steve, we're not going to have to do this again on your 90th birthday, are we?
No, I'm not going to have a 90th birthday. I'm going back to 60 after this. And I'm going to start all on my next 80th birthday.
Yeah.
Okay.
My mother, who passed away when she was 99, used to lie about how old she was. She took 20 years off of it. And it sounded good to me, so I think I'll do that too.
Steve, that is called renormalization.
Absolutely.
Actually, I think it's called making the theory fit with experiment.
You mean fudging?
I guess it is time, and Alfred, do you think we should start?
Oh, I think it depends on you. As soon as you
yeah,
start,
we have about 35 participants, I think. Sunil, Jobin, am I right? We have 35 participants now?
Yes, 35.
Yeah.
35. So I'm sure people will be joining, but it's actually time.
Oh yeah, we
Can we all mute now?
Yeah, so I guess I think we should start because, everybody's on a different time zone and things are quite tight. So we will go ahead and start the session. So
I guess
today,
I can say hello, everybody. Hello, Steve. Hello, Tom.
Hi, Nora. How are you?
Hi, Nora.
Jean-Patrick, hello.
Yes.
Chris Green. Yeah, hello, everybody.
Yes, indeed.
Hello, Nora.
Hello, Eugene.
Hello there, Nora.
Hello. Hi.
Hey, Nora, what is happening now?
Hello, Pranawa.
Yes, hello.
Hello, Alfred.
Hey, Nora. What's happening? I'm losing you guys. Do you hear me?
Yes, we hear
Yes,
you.
we can hear you, Alfred.
Since I have lost you somewhere, Pranav, we can start. I don't know what happened.
Yeah, so that's fine. So I guess we will start the session now.
Yeah.
And we have the session on physics of atoms and molecules in confinement in the session 3. And we have Professor Alfred A.Msezane of the Clark Atlanta University, Director at the Center for Theoretical Studies of Physical Systems, to chair this session. Alfred, of course, is well known to everybody for his work on light atom interactions, non-dipole effects, small angles, scattering, negative ion formation, and so on. So welcome, please welcome Alfred, and you may take over, Alfred.
Okay, and thank you, Prana. Like many of the speakers and organizers, I wish Steve a happy birthday. Now, I've known Steve for over 47 years. I hope and wish that this represents his half-life. Now, I'm glad somebody says that. Now, each speaker will be given about 20 minutes, which includes 17 minutes of presentation and 3 minutes of questions and answers. The first talk here is further thoughts on resonances in confined atoms and ions, and Professor Connerade will be giving the talk. Please, Professor Connerade.
Hello, let me try and get this going. I hope you can see what I'm doing, and if I've got it right, you should now see something on the screen. Is that it?
I can see perfect.
Yes. Well, this is a rather special kind of meeting, of course, and so I wanted to introduce my talk in a somewhat different way, to wish Stephen a happy birthday and to skip all the erudite reminiscences and rather talk about how we met, which was quite interesting, I think. We actually met in a peculiar place. We met in Tashkent for the serious work. I think I'd already met Steve a couple of times before that, but the proper meeting was in Tashkent. And we'd both been invited to this rather unlikely location by a mutual friend, Valeriy Dolmatov, who is one of the participants, I think, in our meeting tonight or today or this morning. And the result of this encounter in Tashkent was that we produced this paper in which we announced that an atom confined inside a spherical shell could exhibit different types of resonances. That's what we were actually doing in Tashkent. Actually, it was quite curious because Steve, of course, was looking very smart in Tashkent, as he always does. And every time he stepped outside in the street for any distance, more than a few meters, he was stopped by the police in Tashkent. The police in Tashkent had no money. I think they had no pocket money. And so when they saw an American professor go around, they thought this was an opportunity. And so he found it very difficult to make any progress at all down a street in Tashkent. And I, on the other hand, had no problem at all because I went along to Tashkent with a very old raincoat. And I looked more or less like the sort of person from whom you could never get any money, whatever you did. And so the police let me pass without problem. So that was one of the recollections I had, which probably Valeriy will remember well. Now, the three kinds of resonances, as I was saying, and the first kind of resonance we identified was an original atomic resonance. This is usually a giant dipole modified by the presence of a confining shell. So what we were doing is really solving Schrödinger's equation inside a sphere. And then, of course, you expect that the presence of the shell changes the atomic resonance slightly. The second kind of resonance we identified is the rather interesting one, because the confining shell, when it becomes small enough, is of course a quantum object. And this quantum object has quantum states of its own, naturally. And so the second kind of resonance is what we call the confinement resonances, the ones which are due to the confining sphere and modified by the presence of the atom. Now, these actually had been forgotten by Sommerfeld, and so that was a rather interesting thing to add into the problem. And the third kind are molecular resonances, which are characteristic of the complete system, and they don't exist otherwise. And they, of course, usually occur in a completely different range of energies. So the two kinds we were most interested in were the first kind and the second kind. And maybe it helps to describe where I was coming from scientifically when I turned up in Tashkent. My interest in centrifugal barrier phenomena came from an early experiment with synchrotron radiation, in which this was done in the Physikalisches Institute in Bonn, where we found we've observed the first giant dipole resonance for a free atom. This was actually not xenon, but barium. Barium was the first atom in which this was seen. And this put paid to an idea when you see giant resonances having been found in solids. People initially thought this was a solid state effect, and it was supposed to be a feature of solids. There were a few exceptional scientists who realized this was not true, in particular Tatiana Zimkina in Leningrad. And so we were able in our experiment to nail the fact that this was really a purely atomic effect and that it's found also for free atoms. The other problem I'd been working on was a unique knife edge situation in barium plus, and I'd like to describe it. And I'd like to describe that a little bit today, and also add that as a fan of Sommerfeld, I've already remarked confinement resonances had been left out in their paper, and so that was worth thinking about. Now, usually we think of atoms as having long-range potentials, that is an infinite number of bound states. And we consider short-range potentials, that is a finite number of bound states, as characteristic of nuclear physics. But this isn't really entirely true. Atoms can have both. And a giant dipole resonance really occurs by exciting to the lowest state in the inner short-range well of the effective radial potential deep inside the atom. So I'd like just to make some general remark about this. You see, actually, you can create, this is a table which is due to Smith and Kmetko, two physicists working on magnetism in Los Alamos. And they were plotting the difference between the conducting, the delocalized and the localized states in solids. And they recognized that this is actually an atomic effect. And so they plotted it as a function of the long periods in the periodic table. What they did is they compressed the F periods and they expanded the D periods a bit, and they produced this rather interesting quasi-periodic table. And this broad sweep across the table is actually the locus of the giant resonances. You recognize that, and it's also the locus of quite a few other interesting things. All the good catalysts are down this. You see palladium down here, cerium, and for example, is used is useful in hydrogen storage. And you recognize on stable behavior, uranium goes superconducting under pressure, and there are all sorts of other interesting features down this table. But I just want to point out the strong connection between solid state physics and atomic physics in this problem. Now, I turn now to this unique case in barium plus that I mentioned. The giant dipole, of course, is, as I said, due to the lowest state inside the short-range well. And so it's relatively stable against changes of environment, and that's why it survives in solids. But, of course, with this double well situation, other things can arise. So here I've taken the Hartree-Fock potential for barium plus. And what I've done is I've fitted it. You see, it's quite a close fit to a Morse potential. Now, the Morse potential has an interesting property. It has analytic solutions. So once you've fitted the inner well to the Morse potential, you can tell where the lowest bound state is. And you see in barium plus already, this bound state is falling between 4F and 5F. That is to say, 5F does not live completely outside. It is becoming trapped in this inner well. And this happens, of course, before 4F drops into the inner well. So here are the wave functions, which Hartree-Fock wave functions for this situation. And you see you have a double well situation with hybrid wave functions, which in fact have there's a lower amplitude of 4F in the inner well and the higher amplitude of 5F, you see. So this is what happens before the 4F state collapses into the inner well. And so barium plus is a unique situation where you have the atom poised on the point where this collapse is going to occur. Now, if you do a bit of theory, if you do a bit of scattering theory inspired by nuclear physics, you can find various analytic formulae, and you see here is the NF series with a very, very anomalous quantum defect. Now, normally you would say, okay, this means there is a perturber somewhere, but there is no perturber at all in this problem. this is the result of the double well potential. And if you do your scattering theory on it, you do short-range scattering theory, you can find a better function to plot. And so you have a modified quantum defect theory which straightens everything out. Okay, and you notice here that this theory indicates that the perturber is down here between 4F and 5F. You see, the 4 is off the curve. Now, this gives you the idea that if you were to move back a little bit further in the periodic table, for example, to cesium, you might actually, by exciting another electron, that is having 2 electrons up in the air, you might be able to control the collapse into the inner well. And so here you have the function in cesium with the outer electron in the n equals 6. And now as you excite this electron up, you see that the 4F wave function, these are all 4F wave functions, by the way, okay? But the 4F wave function changes as you excite another electron in the system, and the 4F function undergoes what I would call controlled collapse into the inner well. A difficult experiment to do, but it gives you the idea that maybe with putting an extra well around the system with a fullerene cage, for example, then you might alter the point of balance and actually control orbital collapse with this outer well. And here is an illustration from calculations Valeriy Dolmatov did on chromium, which is another such critical situation. And you see here the radius of the outer well surrounding, in which we've encapsulated chromium. And you see how by controlling this radius, you can actually precipitate this double well behavior. So you can control collapse using an outer well. That's what the theory tells you. Now, what I'm suggesting, and this is my little birthday contribution to Stephen, that you see, we looked at, when we classified this, we thought, well, the atomic states, they're pretty stable. They're the giant dipole, for example, they're pretty stable. And so we will just see small modification of a particular atomic state when we put a well around it. But what I'm saying now is, well, actually, it's more subtle than that. If we were in the situation where the atom is poised and not quite sure which well it's going to be in, and indeed maybe in a hybrid state between the two, then there's the possibility that the instead of just one atomic resonance modified by the presence of the confining shell, which is what we put in as case 1 in our paper, we can also slide up or down from one atomic resonance to another within a channel by changing the properties of the confining shell around the knife edge. And another perhaps final remark I'd make is that since confining shells are semi-transparent to electrons, the excited state wave function of the confined atom can actually remain poised partly inside and partly outside the confining shell. You can think of this, if you like, as having a Rydberg series, and this confining shell is somewhere in the middle of the wave functions in this, and this, of course, will alter the phase shifts. It will alter the quantum defects, as I've shown you, but in a new way. And so already for barium plus, I pointed out that we needed to introduce a new kind of single channel quantum defect theory. And you see, if we now play the same trick with atoms poised on the verge of collapse inside a confining shell, then there will be plenty of instances where we need to fiddle around with quantum defect theory in order to get the single channel QDT correct. So there's a room for a lot more exploration, Steve, and maybe we get together. Somebody said we were planning to get together for your 90th, and hopefully that will be a meeting otherwise than just by using computers, maybe we can actually meet on that occasion and have a good drink as well. So anyway, happy birthday, Steve, and thank you indeed for all the inspiration you've given us over the years.
Thank you.
And thank you, Professor Conrad, that your slides are so good for some of our eyes.
That's because I'm getting old as well.
Now, are there any questions or comments? We still have a few minutes.
I have one. Jean-Patrick, it's good to see you. I'm not sure I know exactly what you're referring to about the new kind of single channel QDT you introduced.
Yes.
Could you, I don't know, maybe put in the chat or mention at least the journal and year so I could look it up and make sure I am familiar with those ideas?
Okay, I will do that. I mean, basically, what I was doing in this alteration of QDT was using effective range theory from nuclear physics, right? And so this is based. This is really quite simple. It means you try and look at what the asymptotic behavior of the Schrödinger equation is in this situation. I have published that, so I'll give you a reference to it. I will put that. How do I put that? I don't think I can put it in a chat here because I don't have it to hand. But maybe what I should do is include it in the references. I think we're publishing this work as well. I'm not sure, but I'll try and get it back to you.
Okay, thanks. Or you could send me an email.
Sure. Can you send me your email address? Do I have it here?
I think I can find yours, so I'll try to do that.
Yeah, please, and then I'll respond with the reference.
Thanks.
Jean Patrick, do your results depend on the selected potential used?
Yes.
Or they are robust?
On what potential you use? Yes, certainly. All these results. I mean, when I describe things in terms of a double well potential, that is also dependent on what potential you use. Obviously, some potentials tend to enhance this behavior. Hartree-Fock actually does. It tends to enhance the double well behavior. And as you introduce more and more correlations, you basically smudge things out. And so I have a feeling, but there was a nice paper actually, you perhaps remember seeing it, by Griffin, Cowan and Andrew a long time ago. This was based on the Cowan code, and they also, in fact, they came up with some of the earliest calculations showing that the collapse occurred, because you remember there was a paper by Gerpert Meyer a long time ago. She used the Thomas Fermi potential, of course, because she was one of postdocs of Fermi, and the fact that she used this potential had a bad result for her. It gave the double well potential in the F states, but it did not give the double well behavior in the D states. And so she was able to explain the long F periods, the lanthanides, but she couldn't produce a proper explanation for the transition elements in the D periods. And so that's the reason why you find that Hertzberg's rather erroneous ideas about screening propagated into the textbooks, and a lot of the textbooks which are still used actually have this erroneous idea in them. It's only later, it's after Robert Cowan's calculations, that it was realized that Fermi's explanation was actually correct for both D and F states. And so this has now been corrected. I mean, if you take books like Fano's book, for example, that states this correctly. So it is potential, it is dependent on the potential. I quite agree.
I have a comment on that. This is Ravi Rao. Actually, in 1967, Fano and I showed that this happens, of course, with the Hermann Skillman, which is the Hartree Slater. And we had noted that the Thomas Fermi wasn't accurate enough to show it in the D wave. But in some ways, I mean, Fano had that intuition from the transition metals that they were like the lanthanides, and this had to do with the barrier for the D wave.
Well, I think it was more than intuition, because, of course, he'd worked in Fermi's group, and he was well aware of the limitations of Thomas Fermi. So that, I mean, there was actually very interesting work by Majorana on this aspect of the Fermi potential.
So let's thank the speaker. Since we can't, applaud, we can applaud.
Sure we can.
Thank you. And the next talk is how a simple model can push the development of the field from abstractly confined atoms to an ad hoc studies of fullerenes, Professor Dolmatov.
Can you hear me?
Yes, very well.
Yes, we can hear you.
Okay, that's good. Thank you so much for inviting me to give my presentation to celebrate Steve Manson's influence on the field of atomic physics, and also to celebrate his 80th birthday. Steve, happy birthday to you, and thank you for a huge influence on atomic physics from your side. The aim of my talk is, since we are celebrating Steve's contributions, one aim of my talk is to highlight contributions which were made with Steve's participation in the area of research on confined atoms. Jean-Patrick just gave us a brief, very nice introduction into confined atoms. And the other aim is to make the audience who has little knowledge of confined atoms, to make them acquainted at least with few exciting results featuring properties of confined atoms which cannot be met for free atoms.
Question coming.
What are confined atoms and why to study them? Actually, I have learned much from Jean-Patrick Connerade about confined atoms and why they are important. For example, a confined atom is an atom which is placed into a spatial empty cavity whose size is about the size of the height of the atom itself. And it appears that this problem can provide many insights into various problems of significance. For example, like atoms under high pressure, reversible storage of ions in certain solids, which Connerade investigated a lot, changes in chemical valence of atoms, properties of atoms which are captured endohedrali inside Fullerene cages, and so on. So that's pretty much exciting area of research where not only interesting but novel properties can be met which cannot be met in free atoms. And actually there has been a lot of research on confined atoms since long ago, and today there are pretty much comprehensive reviews written on confined atoms which I have listed here. And I want to focus your attention that those reviews include even 2 volumes books and other books, not only journal papers. And one of review papers that we wrote with Manson and Connerade about confined atoms has received very well, has been received very well by research community and got about 200 citations to date. So that's a clear impact of contribution with Steve's participation into that area of research. And I would like to first talk about research that excited me personally very well, and to research to which Connerade has introduced me when I met him and worked with him at Imperial College. We decided to investigate how atomic shells are filled in atoms which are strongly compressed. And Connerade at that time suggested to use a simple model to investigate effect of pressure on atoms. Just take infinite spherical box with hard walls, place the atom at the center of the box, and start playing with the radius of that box to imitate pressure on the atom, and see how configuration of atom will be changed and what properties this compressed atoms will have. So that we did a lot of calculations, and we end up with pretty many interesting results. And I want to make you acquainted with only one of them. But before, I should tell that actually the idea of placing atom inside infinitely high spherical potential wall was not new, and it was introduced, as Connerade has already mentioned, by Sommerfeld yet in 1938. And then it followed by other researchers for various, to investigate various properties, primarily of single electron atoms. So that what our significance of our work with Connerade and Manson was that it revealed some systematic modifications in the filling of shells in compressed multi-electron atoms, and provided insight into the question of which atoms are able to rearrange their structure under external confinement. And we look for some certain atoms from 3D and 4D rows of periodic table. And one of exciting results is related to the effect which is known as SD competition in transition metal atoms, when populations of D and S state compete with each other. So we decided to look what happens to this SD competition if you start compressing atoms. Will they rearrange the structure, or will they maintain the same competition? And here are some of results of our study. So that, for example, take the chromium. The ground state chromium has a configuration 3D quintet for a singlet as a low state. But as you start compressing the atom, that is, as you start decreasing radius, the energy energy of different configurations change differently. And at some point of pressure, it appears that 3D sextet configuration takes over 3D quintet 4S singlet. That is first example that competition between 3D and 4S population has disappeared in chromium. Then we looked at the same situation for manganese atom. And again, in manganese atom, in free atom, this is configuration of the atom. As we started compressing the atom, energies of different configurations were changing differently. And it's already at this point where configuration 3D6-4S took over as the original configuration. That is, one electron prefers now to be sitting on 3D level rather than on 4S. And as we were further compressing the atom, then we arrived at the fact that configuration 3D7 has the lowest energy, and therefore, again, population of atomic levels follows ordinary rule that first 3D levels are populated, and then populated are 4S levels. The same you can observe for nickel. The same you can observe for other atoms with increasing pressure. So that was first very exciting. To me, it was a sort of discovery when we found that the effect known as SD competition can disappear, and we can make it disappear by compressing atoms. And since configuration of atoms now is different from free atoms, then this means that chemistry will take different routes between free and confined atoms. So that was the first thing which we found interesting in confined atoms. Then I should tell you that that work attracted considerable attention. It was one of works that attracted considerable attention about pressure of atoms. And nowadays, the entire periodic table of compressed atoms has been built recently by these authors. So that topic is interesting. As a next level of our study, which John Patrick mentioned as well, was to look at what is happening to the structure and spectra of atoms which are either confined endohedrali, we call it endohedral confinement, either confined in Fullerene cage, in this case C60 cage, or atom could be confined in C60 cage, which in turn is confined in a bigger 240 cage, which in turn is confined in a yet bigger 540 cage, and so on. So-called Fullerene onions, which are arranged like Russian dolls. So when we started looking at that problem, it was novel problem, and that's when we decided to join our expertises to tackle this problem. And we met, John Patrick didn't mention it, but we met either in 1999 or 2000, I forgot, in Steve's laboratory at Georgia State in Atlanta. And I believe that that was with support of NATO grant. When we started working on confined atoms. And we ended up with pretty many exciting results. First, we paid attention how electron structure of atoms could be changed when they are surrounded by the cage like C60, but parameters of the cage would be varied. And we started varying, and we approximated C60 cage by spherical potential of certain radius, certain depths, and certain widths, and placed the hydrogen atom at the center of that cage, and decided to see what will happen to configuration to the structure of hydrogen atom as you start decreasing, as you start playing with the depths of that confining potential. Well, there is some interesting and to somewhat sad story. We actually picked up the idea to approximate C60 cage by this potential from the work of Uwe Becker, devoted to oscillations in photoionizations of empty C60. And then we decided to extend that idea to endohedral fullerenes by placing atom inside that potential. And we are very much happy with that. But it appears that before us, that idea has already been used. And it was used by Puska and Niemann in their study of photoabsorption of atoms inside C60. But in 1998, 1999, we didn't know about that paper. So it didn't, it was not cited in our research. Anyway, what interesting that we found in this system in the hydrogen as we were changing the depths of the well. It appears that terms, ground and excited terms of hydrogen started behaving very interesting. For example, as depth is very small or zero, we have one state as a ground state of the hydrogen atom. As potential depth was decreasing, however, 2s term, energy of 2s term was very, very rapidly approaching the energy of 1s term. And then at some point, they were scattered of each other. And what is interesting is that 2s electron picked up the energy and behavior of 1s electron, and 1s electron picked up the energy and behavior of 2s electron and started falling down with increasing depths of the well, whereas energy of 2s electron remained constant as it was for 1s. And that situation remained until the energy of 3s term, again, it was very rapidly approaching energy of 2s term. And again, at some point, they were scattered off each other and so on. That is, we discovered something very interesting structure of terms of such confined hydrogen atom. And also we indicated the existence of interesting phenomenon that we called avoided level crossing. And after our work, avoided level crossing was investigated in research works by other scientists as well. So that was very exciting, and we decided to keep working on spectra and structure of confined atoms. And we paid attention to confinement resonances, as Connerade told. Confinement resonances, it appears to be that the atom which is inside C60 or in the carbon cage, its photoionization cross-section may exhibit oscillations around photoionization cross-section of free atom. And that was interesting. But again, those oscillations were originally predicted in the work by Puska and Niemin in 1993. And that's where they also used that very simple model potential, where they approximated carbon cage by spherical potential of inner radius, depths, and some certain widths. So that I think at that time, again, we didn't know about that work, and it didn't find, it was not cited in our work. But those resonances are called confinement resonances. The prediction of these resonances after Puska and Niemin was followed by the work of Vendin and Weisberg and our friend Boltinkov, and later by many other researchers, including ourselves. But it was only after our work, which we published with Connerade and A.Msezane, that a better understanding of the nature and origin of confinement resonances was unraveled. And the very name confinement resonances actually was invented by us in that paper and was given birth to life. And now many researchers in this area refer to such resonances as confinement resonances. These resonances emerge, as we showed explicitly, they emerge due to constructive and destructive interference of three waves. One is photoelectron wave, which comes out upon photoionization of confined atom. The other is electronic wave, which is reflected from inner border of C60. And the third is photoelectronic wave, which was reflected from the outer border of C60. So that constructive and destructive interference between these waves gives birth to confinement resonances. That would be in empty C60. And as mentioned Connerade, now there is atom, and the field of atom will change somehow those confinement resonances. And that effect of atom on confinement resonances will depend, of course, on the atom itself and on the parameters of the shell. So that we decided to push our research further by placing different atoms inside the Fullerene cages and investigating different Fullerene cages to study what will happen to such confinement resonances. So that since I'm short of time, what I have only list some most important results of our study on confinement resonances. First, in one of our work with Manson and Connerade, we encountered situation that in the endohedral environment can produce significant redistribution of oscillator strengths in trapped atoms, making the dominant transitions no longer superior, but inferior. And that was discovered by us on the case of calcium at C60. Then we found with Manson something else very interesting. We discovered a new type of confinement resonances, which appear to be multi-electron in nature, and they are induced in outer shells of atoms by confinement resonances in the inner photoionization amplitude. And through interchannel coupling, those confinement resonances were transmitted to outer shell, and photoionization cross-section of the outer shell exhibited confinement resonances as well. But they are of a different nature. Their nature is multi-electron. We also looked in what happens when you place atoms inside endohedral ions, positive or negative, and how that will affect photoionization spectra of such atoms. So there were a number of interesting findings, but to me, the most exciting finding was what we called Coulomb confinement resonances due to negatively charged Fullerene cage. And those resonances dominate the spectra of encapsulated atoms. And what else was interesting for negatively charged fullerenes is that we found that the effect of that shell is to move some of the oscillator strengths of the atom from discrete excitation region into continuum region. Well, then relatively recently, we joined efforts with Anatoly Heifetz and Pranav Deshmukh and his co-authors, co-workers, to investigate how these confinement resonances can affect the time delay in photoionization.
It's time to sum up.
Say it again, please. Okay. How confinement resonances can affect at the second time delay in photoionization. And we found that, yes, time delay in photoionization of endohedral atoms is quite affected by confinement resonances as well. As another thing,
you have exhausted your time now. Please.
How much do I have?
Essentially zero.
Zero. All right, then I'll skip this, and I will tell that not only we worked on confined atoms, but many others as well, including those who are present in this audience. It's Himadri Chakraborty, Alfred A.Msezane, Andrei Solovyov, Jean-Patrick Connerade, co-workers, Tom, sorry, Tom, I might mispronounce your name, Garkusa, Stephen Manson, Pranav Deshmukh, and in the end, the existence of confinement resonances in endohedral atoms has been proven experimentally in recent work of this process, and where again, Steve Manson contributed to that work as well. So that, thanks, Steve. It was a great pleasure and honor for me to participate in many years of cooperation with you, and congratulations on advancing science to a higher and yet higher level on the extensions of over 50 years now. And happy 80th birthday to you. Thank you. I'm done.
And thank you for your talk. We can only allow one question or comment. Any questions or comments? And I thank you, then we can go to the next talk.
Thank you.
And thank you, Prof. The next talk is Probing Molecular Dynamics in Real Time from Within with Free Electron Lasers, Professor Berrah.
Alfred, before you go on, can you just ask all the people to keep their microphone muted because we are hearing some background noise? Nora, we cannot hear you.
Nora, you're muted.
I was waiting for the announcement that you were going to make, but I get started.
Alfred, yeah.
So hello, everybody. I am happy to be invited to contribute to Steve Manson's 40th birthday, because I don't know if you feel the same way as I do, but to me, he looks the same, and I've met him for now a long, long time. So I'm happy to be part of this event. And Steve, I don't know if you remember, but we have about 6 publications together. And among those 6, we have 4 phase rev letters. We have collaborated in 3 topics. The first one was a collaboration with François Vulemier on hollow core lithium. The second one was a collaboration with led by Dennis Lendl in photoionization of atom. And then the third one is on the photodetachment of negative ions, which my group led. And so we looked at K-shell photodetachment of lithium minus, experiment and theory. And I looked at these yesterday as I was making my talk, and I realized that we plagiarized ourselves, because we have said in this abstract that the experiment really revealed dramatic structure difference substantially, both qualitatively and quantitatively, from the corresponding processes in lithium and lithium plus, and the R matrix calculation was used. And so I don't know if you remember, but this was our figure, the most important figure that compared the shape resonances that we measured and the R matrix calculation. And then a year later, we published another PRL on the K-shell photodetachment of helium minus, and we say exactly almost the same sentence. We say we display a dramatic structure differing substantially and qualitatively from the corresponding process in neutral atoms and positive ion. And this was also done with the R matrix calculation. And this was the figure that showed the structure that we measured and the R matrix calculation. And we, in fact, were able to reveal the discrepancy between another calculation, and I'm not going to name the author of the other calculation because her postdoc made a mistake. And so this is not a photoionization session, I know, and I just wanted to bring up these 2 work that we did together, Steve. Instead, I'm going to put my attention into what we've been doing recently, which is time-resolved measurements in molecules using free electron laser. And in particular, since this is the confined session, I will talk about the C60 ionization dynamic that is induced by XFEL pulses from LCLS. So what were the driving questions? Well, we wanted to know the response of C60 subsequent to absorption of intense short X-ray pulses. And we surmised that there would be a particular finding, and that is to bring insight from the spectroscopic measurement into a fundamental question, and that is radiation damage of biomolecules during imaging with FEL X-ray exposure. So to do a pump probe experiment, if we want to do a time-resolved experiment, we need 2 pulses. And we're talking a free electron laser. And so we have an electron bunch, and it is a tour de force for Alberto Lutman to produce those 2 pulses, and I'm going to tell you about it because it's interesting. So the electron bunch comes into an XY dipole, and it is manipulated in controls such as the tail of that electron bunch is on axis. And so when it goes into an undulator, it could laze and give the first FEL pulse. Then this electron bunch goes into a chicane that allows it to have a delay. It gives us a delay for our measurements between 25 femtosecond and 925 femtosecond. This electron bunch goes into an XY dipole moment. It is again manipulated such that the head now is on axis when it gets into the undulator. And so we call this a fresh temporal slice that allows us to have 2 photons. And so when there is no lasing, this is the image of what we have. But if we have lasing of those 2 pulses, we will have the tail and the head of the 2 pulses. So the experiment was done by focusing those 2 pulses into what we call a Kirkpatrick bias mirror to get high intensity, because the idea is to have high fluence and do multiphoton ionization on a fullerene. So the interaction region has our oven, and we use a 2-meter long magnetic bottle spectrometer. We can see here, if we zoom the interaction region, or we can see the length of the time of flight, the oven, and then the permanent magnet. So what did we measure? Well, because we have a very packed pulse with photons, we're able to ionize the parent molecule from C60 plus all the way to C69 plus. This is done through multiphoton ionization. We used photon energy of 640 eV, that is above the carbon K edge, which is 280 eV, allowing for photoionization and Auger decay. And this is where we get this highly ionized parent molecule. We also measured molecular fragment A ions, that is carbon 19 plus all the way to carbon plus. We call them molecular carbon chains, but also the doubly charged carbon 2 plus 31 all the way to C3 plus. I'm not going to be able to have time to talk about any of this. And so the observable that we used is in fact the atomic carbon that are generated during this ionization. And I'm going to do a just flashback to show you the data that we obtained a few years ago when we were at a super high fluence. So at super high fluence, we had carbon into the chamber with 485 eV above the carbon K edge. And we did the measurement at very short pulses, 4 femtosecond, and at 90 femtosecond. At the long pulse, we were able to fully strip carbon, and basically carbon 6 plus were generated. And with the shorter pulse, because we don't have as much photons, but also because we thwart the Auger effect, then we went up to carbon 5 plus. The calculation was done by the group of Robin Centra, and the model initially predicted a more abundant charge state. That is, the yield for the calculation was much more intense than our measurement. And they had to introduce strong recombination of electrons with the ions after the pulse end in order to get this agreement. And so what we show here is the comparison between the model and the measurements. And of course, it's the subtraction of both. And if they agree, then we're going to have something close to 0. Well, what we found at these two different pulse duration, the green is 90 femtosecond and purple is 90 femtosecond, that without molecular effect, it doesn't, basically we don't have a good agreement. If we add bonds, well, the agreement doesn't change so much. But if we add secondary ionization effect in the calculation, we have a much better agreement. Also, if we add bond breaking and if we add molecular Auger, we have a much better agreement. And so what this work showed, this theoretical and measurement, showed that we have a significant secondary ionization by the photoelectron and the Auger electron in C60. And this is completely different from van der Waals clusters. We also found that molecular influence is very strong compared to the van der Waals clusters, and also that the CC short bond length allows for a strong Coulomb repulsion in the strong fluence regime. And so basically what we did was validating a fundamental assumption that charged particles in an intense XFEL behave as if they were classical particles. And so I hope the movie is going to start here. And unfortunately, let me see, yeah. This movie is going to show color-coded what happens when you ionize C60 with strong fluids. Color-coded is the charge states that would appear, but what I'd like to draw your attention is how these electrons, which are colliding with the ions, create highly charged state. And these are the secondary ionization that I talked about that needed to be included in the calculation in order to have a good agreement between the measurement and the calculation. And this was the prediction by Zoltan Jurek and Robin Centra at CFEL. So the most recent measurement that we did at LCLS, all of these measurements were done at LCLS, was at medium fluence. And again, the observable is the carbon ions. We found, but this measurement was time resolved because what I just showed you was time resolved. The very first measurement was not time resolved because the capability was not available at the free electron laser. But now that we have the capability to do pump probe experiment, we show here the charge state, carbon plus, 2 plus, 3 plus, 4 plus, as a function of time delay. As you can see here, the theory and the measurement agree. Blue is calculation, red is measurement. The carbon plus doesn't do much as a function of time delay, but we can see that the carbon 2 plus, 3 plus, and 4 plus as a function of time delay increases for about 600 femtosecond or so and then plateaus out. And we were very surprised by this because the initial calculation predicted 50 femtosecond times. That is 50 femtosecond to have the dynamic. So the first finding was that the fragmentation is not prompt, but it is delayed. And the second finding showed that chemical effects were very important. And in here, it's charge transfer and chemical bond that were very important. The kinetic energy comparison of the measurement and the calculation shows that we had low kinetic energy, about 30 eV or so for the measurements, but about 60 eV for the calculation, and of course, because the calculation is a model. And so let me tell you a little bit about the model, because there's a lot of theorists in the audience. And so the theory toolkit was to use a hybrid classical molecular dynamic model. The model follows both electronic and ionic dynamic in space and time. And the atoms are treated as if they are quasi-free. The atom and ion are like quasi-free electrons, that is, Newtonian mechanics is used, but the rate and the cross-section were introduced quantum mechanically, and the charge interact via Coulomb forces, that is, they use in the model non-relativistic equation of motion. Our first work allowed experimentally to identify the key processes that needed to be included in the model, that is chemical bonds, secondary ionization, and recombination of electron with ions. But in particular, in this medium fluence regime, which is the data you just saw, what was very important is valence to valence electron transfer. That is, that the charge redistributes and the accumulated charge between atomic side, or we call it over the barrier ionization. And this slide shows the importance of including charge transfer. If we show here the model without inclusion of charge transfer, we see that in fact there is no dynamics. That is, as a function of time delay, it's rather flat. For the charge states, blue is carbon plus, 2 plus is red, green is 3 plus, and 4 plus is black. But clearly, when we include chemical effect, that is bond and valence charge transfer, we can see as a function of time delay that the ion charge states increases to about the 600 that we've observed and then plateaus out. So what the model also did is predict something we didn't know. We did not know that in this ionization, we produce a lot of carbon neutral. Red is carbon neutral and blue is carbon plus. And so what the pump only yield showed is that at about 400 femtosecond time delay, the generation of neutral carbon from this C60 molecule that basically charges up to 9 plus and then spews out carbons and ions has in fact thrown after 500 femtosecond more carbon neutral than ions. And so this third finding showed that we had substantial evaporation of neutral atoms. So the model then calculated movie snapshot, that is real space and real time simulation of the dynamic for the parent molecule 13 plus, because the model assumed or found that 13 plus is stable, even though what we measure was up to 9 plus. The y-axis shows the maximum particle displacement. What we want to know in these snapshots is how is the molecule and how are all the 60 carbon atom going to be displaced as a function of time delay, okay? So we have the displacement showed in the y-axis and the time in the x-axis. The red curve is the full model, that is including charge transfer and bonds, while the black model does not show any of these chemical bonds effect that we found very important. At 30 femtosecond, which is in between these two snapshots, we see that the full model predicts that the atoms are going to be spaced out by about 2 angstrom, while the basically model without the charge transfer says that it would be about 5 angstrom. And in fact, at about 100 femtosecond, the model that doesn't have the charge transfer basically would have said that the molecule would have totally been exploded and all of the fragment would have been very far apart. And so what did we learn from this work? Well, we learned that the C60 fragmentation is due to the charge dynamics, and it demonstrated that structural changes remain below the critical resolution of 2 angstrom that is considered sufficient to distinguish peptides from a protein or the basis of a nucleic acid. And this 2 angstrom resolution limits the target damage that is induced by Coulomb repulsion that would otherwise distort the sample before it can be mapped. And so we feel that our work contributed insight to the radiation damage during structure determination of biomolecule. And this is this beautiful picture of C60 exploding. That's also my background that contributes the insight to radiation damage. So in the end, here is what happens. I showed you what we thought was going to happen, but what happens is that the yellow, which is carbon plus, and the gray, which is carbon neutral, it takes a long time for them to space out and to basically fragment. And we had assumed that it would take about 50 femtosecond, but as you can see, the fragment take a long time for them to get away from each other. So in summary for this work, we have found that this time-resolved multiphoton FEL ionization and fragmentation revealed 2 fundamental effects, that is evaporation of carbon atom, and a delayed fragmentation occurs in a continuous way up to 450 femtosecond instead of 50 femtosecond, and that bond and charge transfer are very important. And we believe that we have an insight into thanks to this calculation and spectroscopic work, into the diffraction of protein crystal that would otherwise not have this information. So since it is a confined, the session is confined molecule, I'll tell you a little bit about what we've done. And that is, we have been interested in using endohedral following at the FEL. And the goal was to probe this charge migration between having a molecule inside a C80 cage. And so we've looked at holmium-3N into C80, but also scandium-3N into C80 in order to learn about the dynamic of radiation damage due to the Auger cascade on carbon-bonded system. So what happens? We put this molecule in an FEL and we focus on a holmium-3D ionization. It takes 1530 eV. And so what we observed is the parent molecule singly charged, doubly charged, triply charged, quadruply, and then quintuply charged. And we've also observed that the parent molecule gets doubly charged and triply charged. So for the doubly charged and triply charged, we have the same dynamic, that is doubly 78, 70, down to 50. And we were told that this was never observed, that a parent molecule such as a C80 would throw out 30 carbon atoms from as it cools off.
You have almost exhausted your time.
Okay, then I want to go and do the important part, and that is to wish Steve a happy birthday and to thank him very much for a very fruitful collaboration. And hopefully we all meet in person again for your 90th birthday.
Thank you, Nora.
You're welcome.
Thanks a lot, Nora. That's a very nice presentation. Any one comment or question? And thanks a lot.
Can I ask a real quick question to Nora? Did you guys, particularly in the context of this endohedral system, did you guys see any ICD kind of
yeah. Okay, effect? So yes. And in 20 minutes, there is no time to talk about a lot of things. And I wanted to make a connection with the work that I did with Steve. So we did. So we did a photoionization at the advanced light source, and we saw ICD on scandium-3N into C80, and we have a PRL that appeared last year on this ICD. And so we also have submitted a proposal for the FEL, and we got beam time, which would happen this spring. And it's going to be a measurement at the attosecond level, which is wonderful, right? So we will be able to measure the ICD effect at the attosecond level.
Okay, thanks a lot. Then we need to go to the next talk. Thank you.
You're welcome.
The next talk is experimental studies of photoabsorption by endohedral fullerene ions by Professor Müller.
Okay. You see my slide?
Yes, thanks.
Yes, okay, and I do this. Well, in this theory-dominated session, particularly on confined atoms, I will talk about experimental studies, and I think I want to convey to you how difficult it is to follow the theoreticians in their pursuing these confined atoms. When I prepared this talk, I was thinking, when did I meet Steve the first time? And I think our paths must have crossed the first time at the Paris ICPIC in 1977. And then we met again at Gatlinburg, 1981. Eugene Origin, X-rays and inertial ionization phenomena in 1982. We had lots of interactions at many, many conferences since then. And I think we met all over the world, in China, in Germany, in Australia, and of course the US and so forth. And we have always had common interests. During the last 10 or 20 years, we were both interested in photoionization of potassium-like ions. We were interested in photoabsorption by fullerenes, and of course in confined atoms as well. And before that, we also had common interests in ion-atom collisions and so forth. So our collaboration at the Advanced Light Source came into the field of fullerenes by an experiment in which we looked at photoionization of C60 plus ions. This is the cross-section as a function of photon energy that we found. And we sort of rediscovered the giant dipole plasmon here at about 20 to 25 eV, the surface plasmon. And in that work, we discovered a higher order plasmon as well. And in parallel work, our theory colleagues, whose names are here, also found this higher order plasmon in the photoionization of C60 plus ions in their time-dependent local density approximation calculations. Now, with this first success, we were kind of infected by the virus of confined atoms and of fullerenes in the first place. And of course, the next step was to look at confined atoms, atoms encapsulated in a fullerene cage. One case seemed particularly interesting, the xenon in C60, about which we have heard already during this session. Now, the reason for our interest, for our immediate interest at about in the year 2005 or so, was the following. When you look at photoabsorption by a free xenon atom, you find, you have also heard already, a giant dipole resonance, which is due to 4D, 4F excitation. The resonance covers energy range from 70 to 150 eV. And it's a huge cross-section. Basically, all the resonance, all the oscillator strength of the 4D shell is contained in this one resonance. So the oscillator strength of this resonance is about 10. Not quite, but almost 10. Now, the interesting thing happens when you put the xenon inside C60. And this is a calculation by Müller and others, and Alfred A.Msezane was a part of this. And this is really striking. This giant dipole resonance splits into individual peaks, narrow and distinct peaks. And this was kind of the incentive for us that we wanted to look at such effects. And before I go on, I will give you an experimentalist's point of view of what confinement resonances are. This is the encapsulated atom inside a fullerene cage. Now a photon comes in, photoionizes the atom, and the photoelectron goes out. Alternatively, the photoelectron can bounce back and forth inside the fullerene cage and then also leave, and the interference of direct and reflected electron waves gives rise to confinement And of course, we have just heard there's the bouncing off the inner and the outer surface of the C60 shell, whatever shell it is in the Fullerene cage. The first calculation of the cross-section for a confined xenon atom has been made by Puska and Nieminen. We have heard this today. Here's their result. And then came this stimulating calculation by Müller et al. Very pronounced resonance structures in the photoionization of xenon in C60. This was followed by Dolmatov and Manson. We have heard about this calculation also already 2008. Next, Chen and A.Msezane, our chairman, came up with that green result here. Mathieu et al., a group that also included Steve Manson, calculated that dark green curve. And Chen and A.Msezane used another technique, got another curve. Gorsica et al. Came in. Again, Steve Manson was part of that work. It was the first calculation using R matrix techniques, and it was a non-relativistic R matrix calculation. And a similar calculation has been published by Lee et al. In 2013. And I think it is clear at this point, it would be really nice to have experiments to compare all these theoretical results with. So we thought, in principle, we have a suitable experimental setup to study such things. It's a merged beams arrangement. We have used over the last 20 years 2 such arrangements. One, advanced light source. One, we use presently at Petra 3 in Hamburg at DESY. The experiments I'm talking about have all been made at the advanced light source, at least the ones with xenon in C60. And I will, at the end, if I have time, show a few results that we have obtained in Hamburg. Now, in this merge beams setup, we have an ion source that produces whatever ions we want, with limitations, of course. A beam of ions passes a first bending magnet, and one species, one component of the ion beam with given mass, given charge, given energy is selected and travels here along the merging region. And the beam, the selected beam, is overlaid with a photon beam from a synchrotron. A second bending magnet disperses the ions, separates the ions from the photon beam. The photons go straight on and are measured on a photodiode. The parent ions are collected in a Faraday cup, and the product ions are collected on a single particle detector. The nice thing in such an experimental setup is that you have a clean target beam with given mass, given charge, given energy. And it's possible with such an apparatus to measure absolute cross-sections. Now the problem is availability of endohedral fullerenes. You cannot buy xenon in C60 just from the shelf. So our first experiments with confined atoms were carried out with cerium in C82, just because one of our collaborators, Lothar Dunsch in Dresden, could provide this, could produce it in his lab and also purify it. Here's a picture of cerium in C82, and we have looked again at photoionization. Here's the cross-section. Single ionization of cerium in C82 plus. And we see several features in that cross-section. And in order to understand what is going on here, we have also measured the cross-section for C82 plus, just the empty cage. And that's the cross-section shown as the dashed area here. What we can recognize is the giant dipole resonance, the collective surface plasmon. There's this higher order plasmon, and there's an excess cross-section which is due to the encapsulated cerium, and in particular, it's the region where the 4D inner shell electrons can be excited. one can separate this excess cross-section by subtracting the empty cage cross-section from the measured total cross-section. And here is that excess cross-section. And there's no obvious sign of confinement resonances, something that we had hoped for at that time to see, but there's none. And the reason is, this is now a side view of the cerium in C82, which shows the cerium atom is not in the center of the fullerene. And actually it's bound to the inner surface of the C82. And this prevents confinement resonance to be detected in such a system. So in order to really see confinement resonances, we had to bite the bullet and somehow get xenon in C60. And since it's not available, we had to produce it ourselves. David Kilcoyne has set up this apparatus here. There's an oven containing high purity C60 powder. This was evaporated. The vapor was deposited on a rotating metal cylinder, and the always renewed surfaces of C60 were bombarded with an intense xenon beam from an ion gun. So xenon plus ions were bombarded the C60 layers, and you can imagine only a few of the C60 molecules were converted to xenon in C60. Fortunately, with our experimental technique, we can sort out from a mixed sample the xenon in C60 component. And here's the first experiment that we did. And it's that 4D contribution from the encapsulated xenon as a function of photon energy, cross-section for, here, the production of xenon in C58, so two C atoms have left the cage, and the whole thing is already triply charged. The shape of this measurement, although the statistics is quite poor, the shape is reminiscent of what Muzia et al. Had calculated. But there's a problem. Theory had to be scaled down roughly by a factor of 10 to match what we found in the experiment. The reason is that when you let an encapsulated atom absorb a photon, you don't only observe single ionization, you also observe double and multiple ionization, and you observe ejection of mainly carbon dimers, at least in this photon energy range. So in order to compare theory and experiment, one really has to look into all these different channels: double ionization, triple ionization, ejection of 0, 2, 4, 6 carbon atoms. And actually that's what we did. We have measured 4 of the most important final channels into which the xenon in C60 goes after photoabsorption. We had an improved experimental setup or experimental conditions. We had better samples of xenon in C60. We had to make an effort to implant isotope purified xenon, isotope 136, into C60 in order to get this kind of results. So what we see here is we see cross sections for 4 different final channels. This is the pure double ionization of xenon in C60 plus, double ionization with loss of 1 C2, 2 C2s, or 3 C2s. I've also shown here, or I also showed the oscillator strength contained in these cross sections. When you sum this up, you get about 2/3 of what is expected from xenon. We expect about 10, oscillator strength 10. What we have observed is 62% or so. So we had, when we tried to get a total absorption cross section, we had to consider that we had only seen 2/3 of the oscillator strength that is there. But when we sum up all these cross sections and multiply by 3/2 to account for the missing oscillator strength, this is the cross section that we get. Absorption of photons by xenon in C60 plus as a function of photon energy. And clearly there are nice structures, resonance features in this cross section. And this becomes obvious when we compare this cross section with the cross section for free atoms. These are the blue points. So there are deviations from this smooth giant dipole resonance feature. Valeriy Dolmatov has already shown that these are the confinement resonances. Now, after really a lot of work, we have thus succeeded to show the existence of confinement resonances. There was also a theoretical calculation coming along with that publication here. This was a relativistic R matrix calculation, and it was calculated with the so-called dark code, and the authors were Conor Ballance and Steve Manson, Fatih Hazalou, and Tom Gorsica. And this theory is in quite good agreement with the experimental observation. Now, at the end of my talk, I want to show you some results that we have obtained at Petra 3 in Hamburg. Here, I show you double detachment of negative ions of scandium-3 nitride in C80. And the energy region here is just where there's the scandium L edge. We see two very nice distinct peaks, but they are not confinement resonances. They have a very simple cause, and that is we separate the contributions from the L3 and the L2 subshells of scandium. It is also interesting to look at the carbon K edge of such endohedral molecules. This is again the scandium-3 nitride in C80, this time positive ion, and this is the cross section for single ionization and for double ionization. The two cross sections look different at first sight, but there are features in these cross sections which occur in both single and double ionization. There's this resonance peak here. There's this broad feature which comes up here again.
You have already exhausted your time. So
yes, I will be done in a few minutes. This is the same cake here. And the last result that we obtained, we also used another metallofullerene that was lutetium-3 nitride in C60, in C80. And this gave practically identical cross sections at the carbon K-shell threshold. Okay, end of my talk, at least the physics here. I want to show you all the collaborators in our confined atoms research. It's an alphabetical list. I cannot go through all the names. I want to highlight one of the persons who have contributed to this work, and that is Steve Manson. And with this, I thank you for your attention. And dear Steve, happy birthday and best wishes for the next decade.
Thanks very much, Alfred. We can take one question or so. We have 1 minute left for the questions.
Actually, I have a theorist question. In what the cerium in C80 or C82, I can't remember.
C82.
Said, it was bound to the inner wall. How do you know that?
Well, we as experimentalists don't know it, but there are, let's say, chemists who do calculations to find out what is the best position of the cerium with the lowest energy, and it happens it's at the inner surface of the C82 shell. So that's the problem. I mean, you theorists can talk about, I put calcium plus into C60, and who knows if that remains calcium plus inside. You also cannot put uranium 92 plus into C60.
Yes, with the cerium, if I may, with the cerium on stuck on one side, if it were to stay in that position, you would still see confinement resonances. The reason I think that you don't see them is that it does not stay in one position, but it rattles around inside. I think that probably this is moving.
I don't think. It's really bound to the inner surface. There are other cases where the confined atom is rattling around, but the cerium is at this position.
Well, in that case, you would still see confinement resonances.
I think you would only see them if you would, yes, if you would, so let's say, align your molecule and would look at angular dependent emission of electrons. Then, yes, I agree, then you would see, or you should probably also see confinement resonances.
Thank you.
Okay, thanks, Alfred. The next talk is study of correlation effects in ground and excited states of A at C60, analysis employing Shannon entropy and Coulomb confinement resonances. It'll be presented by Professor Jose.
Yeah, thank you, Professor A.Msezane. Am I audible?
Yeah, I can hear you.
Oh, yeah, thank you. Yeah, I hope the presentation is also visible to you.
Very good.
Yeah. Okay. Yeah. First of all, thank you, the organizers and the conveners of this meeting, that we are having a nice virtual gathering. And also, I'm glad that I'm given an opportunity to present some of my work in this celebration, which is ongoing. So before getting into the work discussion, the reason why we are gathered here, I started interacting with the Professor Manson and collaborating with him since my PhD days. And I'm quite glad and fortunate that I'm continuing the collaboration till today. And I owe a lot to him, and I learned a lot from you, in fact. With that, I wish you the happiest birthday, and I hope this banner would be not bad to wish you happy birthday. Right. With that, I think I'll go ahead and I'll just start discussing the work here. What I'm planning to discuss here is about correlation effects in the confined atom, in particular an atom trapped in carbon-60. And the analysis, for this analysis, we are employing two tools. One is the Shannon entropy, and another is a Coulomb confinement resonances. So as far as the Shannon entropy is concerned, we are looking at the initial state of the confined atom. So the first keyword that is in the title is connected to the electronic structure of the confined atom, whereas the Coulomb confinement resonances, as we all know, and also as a part of previous discussions, is pertaining to the dynamics of the confined atom. Okay, there is one more reason why I have chosen these two works. The common thing of this work is these are based on some of the earlier works of Professor Manson, and I thought discussing these work, which are based on his work, will be a tribute to his contribution, and also I thought it's a symbolic representation that we are relying on his works for our progress, in fact. Okay, right. So let us discuss the first part of the work, which is Shannon entropy and the effects of it, correlation effects on the Shannon entropy in confined atom. I would like to spend a minute on this Shannon entropy. So for any observable measure of uncertainty, we can express via two ways majorly. One is via the dispersion, which is primarily the variance or the standard deviation which we calculate for any observable. And the other is the probabilistic way of representing the uncertainty. And from the dispersion side, it's quite famous, the delta X or delta Px, and the associated Heisenberg uncertainty principle. But from the probability side, we have the information entropy, which measures the uncertainty. Now the question, okay, and then there are several information entropies which are available, and the popular one is the Shannon entropy. And why it is popular is also because it has a close connection with the Heisenberg uncertainty principle. It has quite a lot of similarity with the Heisenberg uncertainty principle. And so this entropy is a logarithmic function of probability density distribution, and this is how we mathematically represent it. So the entropy is an integral of rho q ln of rho q with a minus sign here, and the rho is the probability density in the space that is given. So in fact, if it is a momentum space, rho will be the probability density in the momentum space, and we will get the associated entropy. Now, when the dispersion measure of uncertainty is already in place, why do we need the entropic uncertainty? So the answer comes here. Shannon entropy is an alternative, and sometimes it's a superior formulation of conventional uncertainty formulation. So to put this forward, I would like to show you an example, which is a famous textbook example, which is a particle in a box. Now, next, what I'm going to display are the momentum distributions of different states of this particle in a box. So the panel A shows the momentum distribution of n equal to 1, and is well known that it has one peak centered about momentum p equal to 0. But for higher state, for n equal to 2 onwards, for example, let's look at n equal to 5. This is basically a bimodal distribution. It has 2 peaks majorly, and these are located symmetrically on both sides of p equal to 0. And for n equal to 10, you can still see the momentum distribution is located symmetrically about p equal to 0. Now, if we look at the uncertainty in momentum via two ways, one is delta p as well as the entropic uncertainty. That's what I am going to show next. So before that, let me just discuss this figure once again. So from these figures, except for n equal to 1, we know that the entropy or the uncertainty in momentum will be pretty much same for all the states. It may be gradually varying, because if you look at the range of accessibility of momentum, they are not changing, because the accessibility of momentum is peaked around 2 of the momenta. So the accessibility is not going to be changing. So we would expect intuitively that the uncertainty of momentum as you go from n equal to 2 onwards is pretty much flat, or it's very gradually varying. Now let us look at the two representation. So first is the delta px, which is the dispersion or the variance of the momentum, which is represented by this rectangular bars, open rectangular bars. And counterintuitively, one sees that the momentum uncertainty is in fact increasing linearly, which is not representing the real situation here. Whereas if you look at the momentum entropy, it is almost flat. It is gradually varying, and then it settles down. And that's why the statement now is repeated here. So when the distribution is bimodal or multimodal, the dispersion dependent uncertainty is not a good way to represent the uncertainty. So a solution that overcomes this issue is uncertainty based on entropy. Now, the one statement that I would like to make here is, the more the entropy is, so entropy has definitely a similarity with the thermodynamical entropy, although they are completely different. So as in thermodynamical entropy, if the entropy is more, the system is more disordered. So likewise here as well, the more the entropy, the more the electron probability delocalized. With this concept, Let us look at the focused objective of this work. We are going to look at the Shannon entropy of endohedral atom to benchmark the correlation effect. Now, here comes the connection. We have, in fact, based this work on one of the earlier work of Professor Manson, and I'm glad that the co-authors in this paper are also present in this conference. And in this work, the beryllium atom and the magnesium atom, they were kept in the confined environment, and the correlation effect was studied as the correlation environment was varied. And this was one result from this paper. And the correlation energy was so if you look at the energy scale is negative, so there is a minimum in the correlation energy at around a particular, say, 0.6 atomic unit of well depth of the confinement potential. And so this minimum in the correlation was connected to the electronic distribution. Now, here is the connection that we are trying to bring. So if the correlation energy or the properties of the correlation energy is connected to the electronic distribution, then of course the entropy is also connected to electronic distribution. So from that sense, we can try to bring a connection between correlation energy and the entropy. And this is in fact the objective of the present work. And we have taken beryllium at C60. Of course, magnesium also was taken, but for the present discussion, I'm only including beryllium. And the model confinements, and okay, we are not doing any ab initio calculation for the C60 environment. Rather, we are using a model potential, and the confinement is represented by a Gaussian annular square well potential, which is a combination of Gaussian and the square well potential. Now, this is also motivated by the works of Puska and Nemanin, and already the mention of this work has come in today's several talks, as well as I think the similar potential is being employed in the work of Professor Himadri Chakravarti, as well as he discussed in yesterday's session. And this is the model that we have employed, which is mimicking the Puska-Nemanin potential, which is via the Gaussian annular square well model. And for the correlation study, we have used three configurations of the beryllium, and we have used a multi-configuration Dirac fork. And the first configuration is the most probable configuration, which is a single configuration. And then we have excited 2 electrons to the nearest excited states, and we have got 2 different configurations. Now, the point here is, for all these configurations, of course, we add more correlations in to get this different configurations, and the densities or the electronic densities are different. So we can have a representation of the electronic density, which is altered electronic density due to the correlation, as an absolute difference between MCDF minus Dirac fork, and this is the correlated electronic density, which is an additional density, or not addition, because of course the rho is normalized, but this is an altered density, we can say. Now we represent the correlated entropy via this correlated density, and we find the correlated entropy. All right. Now let's look at now the probability density variation of beryllium at C60. If the depth is very low for the confinement, we get pretty much an atomic distribution itself. So this is very similar to free beryllium. But as you increase the depth, we see that the charge is migrated to the well side. And as you still increase, you see that there are two peaks which are developing in the distribution. One is around the atomic region, and other is around the well region. And if you increase further, the charge is getting drifted to the well side, and with further increase, you get that the electronic density is stuck up mostly in the well region. So the left hand figure was for the probability distribution of the 2s electron, whereas the right hand figure is for the 2p electron. So we see a similar variation for the 2s and 2p. So but okay, so what it means is the original beryllium at C60 in this model calculation is represented as a linear superposition of atomic wave function and the C60 wave function. Now, if it is represented as a mixture of these two wave function, definitely the entropy or the uncertainty or the disorder in the system will be more, and of course the entropy and the uncertainty will also be more. That's why we have employed a Shannon entropy look at the system, and entropy is expected to increase for the mixed state for obvious reason. Now, let us look at the Shannon entropy variation for this beryllium, and this is where we look at the figure, right? So here we have the radial entropy variation as the depth is varied. We'll see that the entropy is linearly varying, and then it flattens. So the increase in the entropy is just due to the drifting of the electron from atomic side to the well side, and this is clearly represented here. Now, a similar variation is of course happening in hydrogen at C60 as well, but as mentioned in Professor Dolmatov's presentation, hydrogen at C60 is more interesting due to avoided crossing, and we have in fact seen avoided crossing in Shannon entropy also. This was already published and recently. Now, another interesting point that we look at from this figure is entropies of Dirac-Fock and MCDF distributions are different, which in fact says that the entropies are affected due to the correlation. All right, now let us look at the effect of correlation on this entropy. So here we have the correlated energy, and we see for the two configurations, so C1 and C2, how do we find the correlation energy? We subtract the MCDF energy and the Dirac-Fock energy, and this is where we get pretty much the similar qualitative feature as given in the Professor Manson's work. But C1 and C2 gives a different correlation energy. Of course, it is predictable because C2 has more correlations included in it. And now let us look at the correlated Shannon entropy, and we see a good connection that wherever the minimum is there in the correlation, we also find the entropy also minimum. Of course, this is true because we are looking at the correlated density, and if the correlated density is minimum, that means that the correlation energy is also minimum, or the MCDF density is much alike to the Dirac-Fock density. So with that, I think I will conclude the first session. Now I'll have a brief discussion about the second part. So the conclusion from this work is Shannon entropy is an indicator of correlation effect. With that, let me go to the second part, where we look at the Coulomb confinement resonances and the effect of it on time delay. And as I mentioned, this is about dynamics of carbon-60, dynamics of an atom trapped in the C60, and we look at the photoionization of atom trapped in C60, and this is schematic representation. And here the C60 is mostly represented again in a model calculation. We represent it by an annular square well, and these are the famous parameters that are employed. Now, to get a complete knowledge of the photoionization process, we look at the photoionization cross-section and the time delay, and the time delay is of particular interest for this in this work. And the objective of this study is to look at the time delay due to Coulomb confinement resonances. Now, coming to Coulomb confinement resonances, this is again an idea which was originally put forward by Professor Manson and Dolmatov, and this is where the connection is coming again, as I mentioned earlier. So in this work, the atom encapsulated in not in neutral fullerene, but in anionic fullerenes, they have established that there are this additional resonances which are supported in such system. For example, look at the figure which was taken from their the reference. If you look at the free neon cross section, it is pretty flat, but for the atom trapped in the free fullerene, the neutral fullerene, it gets oscillated about the free cross section. But as we trap them in the anionic fullerene, it gets additional resonances, which are called the Coulomb confinement resonances. And the reason is the following: as we are making the environment more and more repulsive, or when I am adding more electrons to make the C60 repel or kind of negatively charged, it gets this the barrier enhanced. Now, the enhanced barrier, of course, can support resonances, and these are the Coulomb confinement resonances. So for this study, we have employed, or we have used argon at C60 with Q equal to -4. The overall charge of the C60 is -4, and the argon is trapped in this anionic fullerene. And these are the model confinement that we have employed for the C60. So this is basically a hybrid of C60 and the additional charge on the fullerene, and the cage is represented by the annular square well, but the excessive negative charge is represented by this electrostatic considerations, and this was employed in Dolmatov and Manson's work, and we have employed that also. So the effective representation of the potential or the confinement is the cage plus the charge, or due to the additional charge. Now, let us look at the result very quickly. And we have employed a relativistic random phase approximation. And the title, as mentioned in the title, we are looking at the correlation effect. So here also we are employing relativistic random phase approximation to look at the final state correlation effect via the interchannel coupling. And of course, the Coulomb confinement resonances is coupled to other channel to give the effect of it in different subshells. So we look at the 2S and 3S cross section.
You have about a minute to sum up, please.
Yeah, I am just summing it up. Okay. This is mostly my last slide. So this is a 2S cross section where you have two Coulomb confinement resonances. But if you look at the 3S cross section, the blue curve represents the coupled one. You see that due to the interchannel coupling, the Coulomb confinement resonances is coupled here. And then we look at the time delay. And in the time delay as well, in the 2S, we look at the resonance, the effect of resonance on time delay. And due to interchannel coupling, of course, in 3S as well, it is coupled. Now, with that, I summarize here. From the first part, we have looked at the correlation entropy, and it's a good representation of the correlation energy. And the second part, we have looked at the Coulomb confinement resonances and how is it impacting on the time delay and due to correlation effect. With that, let me acknowledge my students in IIT Patna and my collaborator, Dr. Hari Verma from IIT Mandi and his students, and Dr. Angur Mandal from IISA Mohali, and of course, Professor P.C. Deshmukh from IIT Tirupati, and Professor Manson from GSU. With that, I thank everybody, and once again, happy birthday, Professor Manson, and thank you a lot.
And thank you for the nice talk. Are there any comments or questions?
Can I ask a quick question, Jobin? This is Himadri Chakraborty.
Yeah, sure.
So you said that your C60 potential, you are using the depth of Puska-Nieminen potential, which is which also includes a large number of C60 electrons.
Correct.
So effectively, my sense is, and I'll probably have to discuss with you later more, that even though your phenomenon may be correct, but it may be overestimated quantitatively, because the actual atomic electrons would not see such a deep potential. It will see whatever is left after C60 electrons fill that in from the bottom, 200, and keep that in mind that there are 240 electrons to fill it. So it will just see a very shallow energy region to actually collapse into.
Sure. Yeah, Professor Himadri, in fact, we have taken this model, but as you have noticed, we have not taken the depth, in fact. So we have varied the depth to look at the different parameters, for example, Shannon entropy. So it was like a systematic study of how the potential is affecting the entropy. But here, the point is, at least the Puska-Nieminen potential is giving us a kind of a diffused potential, which may be a realistic representation of the C60. So that is why we have adopted this Puska-Nieminen potential to start with. So we have not, in fact, taken the actual depth, as you have rightly pointed out. Probably we may be overestimating if we look at the actual, if we take the actual depth. So, but we have varied the potential from 0 till around 1 atomic unit to look at it systematically.
Okay, thank you.
Yeah, thank you. Right.
Thank you.
Thank you.
The next speaker is, or the next topic is numerical simulations of storage and thermometry of ions in a 16-pole ion trap and a 16-wire ion trap. Professor Kumar.
Hello, can you hear me?
Yeah, good.
Okay, thank you. I hope presentation is also visible.
Yeah, very good.
Okay. Greetings to everyone. This talk is slightly of a little bit different from whatever we have been listening to so far. So we heard a lot about the confinement of atomic systems or molecular systems within actually a quantum confinement. But this talk is going to be different from a quantum confinement. It is actually a classical confinement. I'll be talking about ion traps. The ion traps which we want to use in our laboratory to store to basically to understand more about their properties, the interaction with the photons, maybe even a confined atom, a confined ion within an ion trap. Okay, so why do we need to confine ions? There are various studies one can perform using confined ions. For instance, if you want to know a little bit about something about the ions, we need to interrogate with the laser, or we need to have some kind of. So actually, ions, we can have them spatially placed at some place, and so that we can actually get them more and more, get more details about it, rather than follow while it is on the traverse. So for spectroscopy kind of study, like absorption or emission spectroscopy, fluorescence, one of the is similar to an emission spectroscopy, and then we have photo detachment or photo dissociation spectroscopy. One can also do ion molecule reactions within the ion trap. This is especially important when it comes to gas phase formation of molecules in the interstellar medium. Or one can also measure the absolute photo detachment or photo dissociation cross sections. Photo detachment cross sections have been already measured in some using the ion traps, but dissociation cross sections have not been done so far. This is what we will be focusing on in our laboratory in the near future. So here I would like to start with the working principle of a multipole. It would be better to start with a very simple model. Like we start quadrupole with which is a linear quadrupole consisting of 4 rods supplied with a radio frequency voltage on it, so that adjacent electrodes will have a opposite polarity. So this picture will here you can see so here there is a video which shows how the potential varies on each of these electrodes. You can see that whatever potential formed inside here is a quadruple potential. This is basically a saddle point inside, and when an ion is in there with the proper velocities, it is possible to trap it, because the ion will move towards towards one of the electrodes which has a lower potential, but by the time it moves towards it, and that potential changes again, so that the ion effectively sees a kind of a confining potential inside. So in the case of a quadrupole, it will be R square potential. So the effective potential inside a multipole ion trap, that is a radial potential which I am talking about, is given by this expression where we have the n order, that is 2 for a quadrupole. Q represents the charge, V0 represents the amplitude of the radio frequency voltage that is applied, M is the mass of the ion that we want to store, omega is the angular frequency, and R0 is the inscribed radius, that is the minimum distance from the center of the trap. So the quadrupole is good for several applications, but there are several other type of multipoles that are used, such as the ones having 22 electrodes, that is a 22 pole. We will come to that soon. So here, this is how the potential varies within the trap. So adjacent electrodes will have the opposite polarity. So why do we need such a kind of a multipole trap? It will be clear from the next slide. Here itself, you can see that inside the potential is more or less flat. and the electric field will be more or less nearly zero, unlike the case of a quadrupole. So this is a picture of the famous 22-pole trap. This is designed by Dr. Gerlich. So kind of a trap is being used in several laboratories, which is used for several kind of studies, such as spectroscopy, ion molecule reactions, rate coefficient measurements, and to do experiments like that. So this is one of the most widely used design, and why such a trap is required is more clear from this particular plot, where the effective potential is plotted as a function of the distance from the center of the trap. You can see that for a quadrupole, this goes as r squared, and when you go for higher multipoles, you will see that this becomes flattened out, and then you will get a nearly a flat box-like potential for a 22-pole trap, which means that there is a lot of field-free region within the trap, so that you can have a lot of ions stored within an ion trap. However, a conventional design restricts the access of the ions from the lateral side. So it's because the rods are very closely packed, so you cannot access the ions from the sides. So what you need to do is to access the ions along the axis of the trap. This actually limits the use of such a trap. For instance, you cannot do fluorescence measurement using such a trap. It will be very difficult to do something like that. And also to measure the absolute photo detachment cross section using axial setup, where we don't have the traps that can be located away from the axis of the trap, axis of the setup. You can't have a proper access to the ions that is stored in the trap. So what we plan to do, which is already, which is not idea, but to replace these rods with the wires and try to see how changing the rods to wires actually change the ions inside the trap. So in our laboratory in IISER Tirupati, we have already built a setup which awaits on a wire trap that we are currently building it. And we first want to do several simulations to see how the characteristics of this trap is compared to a 22-pole trap. So the idea is to basically to compare the differences between a 22-pole trap and a 16-pole trap, and of course then a 16-pole ion trap within a wire trap. So instead of a pole, which is a cylindrical rods, we can use wires. We can have the lateral access to the ions. So we will study those using storage efficiency, in terms of storage efficiency, ion density distribution, and thermometry of the ions. So here is the design aspect of this particular trap. So here is the CAD rendering of the design. It is a 16-pole trap. And this is the simplified design which is used for the simulations with the 16 rods placed on in the form of a cage. 2 electrodes on both sides. Those cylindrical electrodes will act as end caps, which will have a DC potentials applied on them, whereas the RF potentials is applied on these electrodes, cylindrical electrodes. So both of these traps, we have chosen to have the same inscribed diameter. So then the rod diameter will be decided by this particular expression to have a proper potential within the trap. So in the simulation schematic is like this. So we have so this dot represents the ion cloud. Outside the trap, temperature, the pressure of about -6 10 to the power -6 millibar. Within the trap, have a higher pressure of the order of 5 × 10 to the power -4 millibar. This is because in trapping we use some inert gas such as helium at a higher pressure, so that the ions with a higher energy going into the trap will collide with the gas, that their energy will be reduced, which will assist in trapping. So first of all, the end cap electrodes will be at the entrance end cap electrodes will be at a negative potential. So the red line represents the negative potential here. So this is the potential axis. This represents. So even though this RF is applied, so the average will be 0 voltage, and the end cap, the exit end cap will be at a higher positive potential. So now, once the ions go inside, it will get slowed down when it nears the end cap here, and then it comes back. By the time it comes back, we raise this potential so that the ion will get confined in the ion trap. So we will store them for a certain period, and then we can lower the potential on the exit end cap so that the ion can be extracted. So that's the schematic of that simulation. So we use Simeon to simulate the ion trajectories within the ion trap and to record the ion characteristics. And the buffer gas cooling is modeled by hard sphere collision model. So we start with an ion of mass 205 atomic mass units because we are producing biomolecular ions in our ion source. Right in the beginning, we will be doing experiments with biomolecular ions. So we take this as a model system. And the ion energy chosen to be is about 2 electron volt with the Gaussian distributed energy with 1 electron volt full width at half maximum. This is all governed by the settings. And the storage efficiency is defined as ion extracted divided by ions initialized. And this can actually depend on several parameters, but once again, this is all chosen by the experimental parameters. The temperature is found out by recording the speeds of the ions that is present inside the trap, whereby when the cooling happens, so the temperature of the ion will slowly decrease, which we will see soon. This happens. So these temperatures also can depend on RF amplitude and cap potential and so on. So we will choose certain variables as fixed and then we'll study the variation. So in this slide, what you can see is the speed distribution of the ions for different times, different storage times means. So this broad distribution essentially represents the ion speed distribution at 1 millisecond, so that your temperature is about more than 1000 Kelvin. And then as the time increases, so basically when the ion is colliding with more and more gas molecules within it, so the temperature decreases. So we can actually fit it with the Maxwell-Boltzmann distribution and see that the temperature slowly decreases. Say 10 millisecond, it is more or less flat. And the average temperature is around 346 Kelvin in this case for a 22-pole trap. And we found that for a 16-pole trap with the similar characteristic, the temperature was slightly higher, around 367 Kelvin. For these temperatures corresponds to the buffer gas temperature of 300 Kelvin, which is very well known that the ion temperature will be higher than that of a buffer gas temperature due to several reasons of a trapping characteristics. So here what we have is a comparison of the trapping efficiency. As you can see, the trapping efficiency is better for a 16-pole trap compared to that of a 22-pole trap. This was a kind of a surprise for us, so why that happened. However, the temperature is lower for the 22-pole trap compared to that of a 16-pole trap. So therefore, had looked at this effective potential. So you can see that the effective potential is more steep for a 22-pole trap compared to that of a 16-pole trap. And there is also one more parameter which is referred to as adiabaticity parameter that determines the stability of the ions within the ion trap. And we have a steeper rise for the 22-pole trap. Now, this means that if the stability parameter is, say, about to more than 0.3, that means that the ions can be more unstable, because below 0.3 we get a more stable operation, but above 0.3 it will be higher. So you can see that depending on how far the ions extend within the trap, the stability parameter can be different. So based on these two plots, it is possible to understand why these numbers at least qualitatively we can understand why this trapping efficiency and temperature are different. Now I'll come to the trap design with the wire trap. So instead of a normal trap with where the inscribed diameter follows this relationship, we are planning to make a wire trap with 50 micron wires. And then we need to see whether this kind of a trap can actually work as effectively as a the rod trap. So here is the design for the simulations, and both of them will have the same inscribed diameter, and every other parameter will be kept constant, and then we will do the simulation and see what happens. So what we have found is that the 16-pole trap has the temperature about 367, which we have already seen. And when we look at 16-wire trap with the same setting, the temperature is same, the uncertainties. So that is a good thing. So we are not really increasing the temperature of the ions. But what about the trapping efficiency? But we have found that the 16-wire trap appears to have it appears to be more efficient to store the ions compared to that of a 16-pole trap. So
about a minute and a half.
Yeah, okay, I'm almost done. Yeah, so if we look at this spatial distribution of the ions, the ions within the pole trap and the wire trap, we see that at lower time scales, the axial distribution seems to be long within the pole trap, and then it compresses within after say 20 millisecond or so. Whereas in the case of a wire trap, this is compressed even more. However, the cross section is much higher. So you can see that there is a more space which is available for the ions within the wire trap. This could be an explanation for why the wire trap can actually store more ions. More efficiently. So now, just to compare the RF amplitude and the frequency characteristics of the ion trap, we have found that so the RF wire trap will need a slightly higher potential than a trap to have a similar the storage efficiency. Also, the frequency characteristics show that so there is a small window which is available for operating the wire trap where we will have the similar efficiency. So to conclude, what we have found is that the wire trap can be a good alternative to the pole trap with much greater advantages to have a better storage efficiency and nearly unobstructed lateral access to do laser-induced measurements such as fluorescence measurements. Temperature of the ions is found to be the same within the pole trap, within the two traps, and the disadvantages can be like making the wire trap can be far more difficult. Also, at very low temperatures, the cooling the wires will be also challenging. So these are mainly two things which can be a problem with the wire trap. But we believe that we can actually kind of get rid of these problems. Now, I would like to conclude with this talk with one of my first publications from my PhD thesis. So this is with the Professor Steve Manson. So that is on the spin orbit interaction activity coupling. That was the theory work which I had done. I mean, during my PhD times, I was doing theory. So there I had a lot of opportunity to interact with Professor Manson. It has been really great to talk to him. It's such a very active person, always as he is, I mean, whenever I meet him. So it has been always motivating for me. And thank you, Professor Manson. Happy birthday. And thank you all for your patience.
Thank you for the talk. We'll take only one question or comment. If there are no questions or comments, we'll proceed to the next talk. Thank you very much. Yeah, the next talk is from models to full molecular calculations by Professor deCleva.
Thank you. Do you hear me? Yeah.
Yes.
Okay, fine. Well, it's a real privilege to take part in this meeting in honor of Professor Manson. So I joined the others in wishing here him say happy birthday and a lot of more exciting years of research. And thank you also, Nora and Alfred, for allowing me to take part. Well, I did some studies on endohedral fullerenes pretty long ago, then moved to other things. Then a few years ago, meeting Steve at a few congresses, we talked together, and he suggested that we took up again the subject to look into some more details. So there are just a couple of things that I want to highlight. That spherical models capture a lot of the physics of those systems, but there are a few things that are typical molecular and that got lost. One you can see here already in this older study of calcium.
Piero, we can't see your slides.
You don't see the slides?
No, we don't see them, no.
Let me see. Share screen.
Yeah, there you go.
It's
that's good.
Okay, great. Thank you. Sorry for the inconvenience. Okay, again, calcium 1s photoionization in C60. Of course, the photoelectron wave starts as a pure P wave at the origin, then propagates, but when it hits the cage, this is for 3 increasing energies, you see very little here additional partial waves, but if you enlarge, say cage is about 7 atomic units, so here you can see that more partial waves get excited. It's up to L11 in this case, with the amplitudes rather comparable. And because they are scattered by the cage, and you can also appreciate even better here, a P wave, when it hits the cage, a lot of angular nodes get excited.
Piero, you can actually go full screen.
Yes, sure. Does it work? Is it better? Okay, thanks. Well, before going further, just 2 words about what we do. We just computed the continuum electron by basis set expansion, not finite differences. Our basis is just the product of spherical harmonics and B-spline radial functions that many of you are familiar with. Anyway, they are this kind of bell-shaped function repeated. They can approximate extremely well any smooth function. The advantage of a basis is that in addition to a longer range one center expansion, which would be the same in atomic calculation, you can also put the functions around the nuclei, and this gives very rapid convergence to full molecular calculation. Okay, after an initial study, Steve suggested that we looked a second time into just the free Fullerene to get a very precise description. This is just the total cross-section. The blue is the best experiment available. The red is time-dependent DFT, and you can see that it follows pretty well the experiment. The black is pure DFT, no response, which is still not too bad. I'll go back to that in a minute. Unfortunately, there aren't very many experiments for the partial cross-sections. Those are pretty old data by the late Uwe Becker for HOMO and HOMO-1 ionization. Cross-section is again quite accurate, beta not so good, which is perhaps strange because the higher energy part is generally easier than close to threshold. Maybe it could be remeasured. Okay, let me just show and enlarge the view of the difference between DFT and TD-DFT. My point here, which maybe will be controversial, is that there is not a big difference. TD-DFT is larger, but even at the maximum, it's a factor of 2, not an order of magnitude. The structure is similar. Also, I remind you that in DFT, there are a lot of discrete excitations which do not appear, but appear as autoionizations in DFT and bring up the cross-section. So my point is that really there has been a lot of, say, talks, discussions about very strong plasmon resonances in C60. We had also before. Personally, I don't believe that. I believe that the origin of that is mainly theoretical. One of the defects of simulating the cage with a potential well is that the electrons inside the well are very mobile. So response effect are very much increased. In one of the studies that was cited, say, the last author was Rost. They going from LDA to LDA, which is the same as DFT and TD-DFT, they got a very large enhancement. But if you take the full molecular potentials, in those covalent systems, electrons are held very tightly by the cores. So mobility is much reduced. There are still surprises in C60. This is very new, and we have still to understand. This is a very fine scan of the total cross-section, just at the DFT level, but we have seen that it's rather realistic. And I was really amazed by this array of very sharp shape resonances. In DFT, you can describe only shape resonances, which I have never seen in any molecule, even of comparable size. So in a way, there must be virtual state very localized in energy and very little interacting with the continuum. Which is something that really we have to look into it. Of course, it is a model. In reality, nuclear motion and other effects will smear that, but still it's realistic enough to point that the existence of exotic states. Other people have talked about exotic states in C60, but it's still something to be fully understood, I think. Well, this is close to threshold. If you go instead on a large energy scale, well, then the cross-section is just 6 times 60 carbon atoms, and without much structure. This is in the total, but if we look at the partial from individual orbital, there are, again, this is well known, no? Interferences and oscillations in the partial cross-sections. Experimentally, what has been measured more clearly is the ratio between HOMO and HOMO -1. And you can see that it's reproduced pretty well. Of course, experimental points are scattered at high energy. So, and I was curious to see how long this persists. And again, if you believe to the calculation, it's pretty regular, apart from some substructure here. They attributed then of scattering from the inner and the outer of the model. But then about here, there is an important damping and the thing is dying. Forget about this pointer, which is just a numerical artifact. Okay, let's move to endohedral. We redid argon in C60 to see the differences with the model potentials. Okay, DFT and TD DFT makes a lot of difference in free argon, but as you can see, rather little again in the confined atom. The confinement resonances are typically a potential effect, so response doesn't do much. And here is 3S, and again, the same story. I'll be very short. That was also computed at static exchange by Jose and Lucchesi with very similar results. Okay, my last thing is a very small study that I did just for this meeting. So nowadays it's possible to encapsulate small molecules by a kind of chemical surgery. Chemists, by the way, I'm a chemist, very smart. They can open a hole in the cage, put in a molecule, and then close the cage again. So this is, again, a model study. I took nitrogen and the core nitrogen ionizations because the energy difference is larger. So in principle, they could be experimentally seen. This is 3 and 2. The two Gerade and ungerade core orbitals, which apart from the sign difference, are extremely similar, of course, but the Gerade shows a rather huge shape resonance. Again, this goes back to Dylan Dimmer, I guess, and it's also confirmed experimentally. What about if you put that into C60? Well, confinement resonances, as one could expect. Again, the original shape resonance is washed out, but say a lot of sharp resonances appear. What I found curious, but it's actually quite easily understood, at least qualitatively, is that the two different initial states give rise to two series of resonances which are interleaved. The blue one from the sigma U is very irregular. The one from sigma G is more complex at low energy, but this is the energy of the native shape resonance in sigma G, so they combine somehow. But then the situation is very regular. Okay, I plotted here also the sigma G, sigma U ratio, because this is what has been measured in 2, and then it's even enhanced with very neat oscillations. By the way, also in 3 and 2, this shows very large scale oscillations, the famous Cohen-Fano resonances. that have been seen, but you see in this scale is hardly visible. So the confinement resonance really a huge effect. Okay, same story for the angular distribution. Again, the deep due to the shape resonance in sigma g, but then they increase very rapidly to go close to the asymptotic limit of 2. And in the confined system, again, the picture is completely changed. Again, here the thing is different because the the results for the two symmetries are very similar. You can see this dip. So the large scale pattern is very similar. There are superimposed substructures due to the confinement resonances, but the overall pattern is very similar for the two symmetries. Well, I played a bit more, looking also to the 2 sigma g. The overall story is the same, but what I wanted to compare was the 1 sigma g and the 2 sigma g. In fact, both in the free molecule, they are similar, show the same resonances, and also the confinement resonances.
You have about a minute to sum up.
Yeah, I'm almost done. And even the angular distribution is very similar. So the main difference is due to the different U and G symmetry. Okay, this is something that in a way is obvious. The photoelectron waves interact with the cage. Also, the cage has orbitals of U and G symmetry, and that gives the two sets of results. So, okay, my small take-home message is, first, most of the physics can be captured at the density functional level. This is good because density functional is still computationally rather cheap, so you can afford rather complicated systems. Even larger wouldn't be a problem. Molecular features are important. The most important is that electrons are tightly bound to the atomic core, and in chemical bonds in those covalently bound molecules would be different for, say, a cluster of alkalis. And in particular for photoionization, the cage gives a very strong scattering of photoelectron waves, not only radial, but also angular. And again, that can be treated accurately for many systems. And as an aside, there may still be surprises to be seen in the manifold of excited states of C60. Perhaps there's something not completely understood. Thank you.
And thank you very much for the talk. And are there any questions, comments?
So how do I?
Now, if there are no questions and comments, let's thank all the speakers for their nice presentations.
Well, that brings us to the conclusion of session 3. And we have the next session coming a little more than 13 hours from now, I think, which will be session 4. It will be on structure, dynamics, and interactions of ions. And Professor John Costello will be chairing this. Professor Anatoly Kaifets will be the co-chair. So there was a little bit of gap between session 2 and session 3, but now the session 4 is a little quicker. So look forward to see you all in just over 13 hours from now. Any other comment or?
Well, just the gap between 2 and 3.
Can't you fix the time can't be constant? It's amazing how much it rapidly changes.
Yeah, this
shows you what relativity can do.
Oh my God.
No, playing with this global timetable has been really tricky, and we did our best, but I'm sure it could have been done better. But that's what we have now.
Well, maybe the world should do what India does. See, India has the entire expanse east to west in one time zone. Maybe the whole world should be in one time zone.
Yeah, but it is.
I think you did a great job, Pranawa. You all did a great job. It's very tricky with all of us in different time zones. So thank you so much for organizing this meeting. I think it went really well.
Yeah, the biggest prize.
I agree with you, Nora. Thank you.
Yeah, well done. Yeah.
Absolutely. Well, kudos to the organizers. Absolutely.
The biggest price we have paid, I think, is that we could not have sessions on all the topics that we would have liked to include. Means, of course, Steve has contributed to these 5 areas and even more, but we could not have those sessions scattering, for example, quantum collisions in a big way, although they come over here in different ways. But there are many areas that we could not include because we needed to restrict the sessions to not more than 3 hours. In fact, we thought that we will do with just 2 hours, but it is already difficult with different time zones. So that's the price we have had to pay. So anyhow, so see you all a little over 13 hours from now, and goodbye for now.
Okay.
Bye.
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 Take care.
Bye-bye.
Thank you.
Thank you.
Goodbye.
All the best.
Thanks, everybody.
Thank you again.
Goodbye.
Thank you.
Nora.
Mm.